Cool. Yeah, so I mean, I'll get into Passive House and talk about it, but I guess generally it's like LEED in that it's a voluntary standard, but we think of it more of as like a building code almost than a checklist. So there's only, and we'll get into it, there's like 5 things you have to do, and you have to do them, and the result is a reduction in energy use of up to 75% compared to a conventional building. And that's it. There's not, nothing about urban site design or water or anything like that. And it's kind of on us to make sure that the materials are healthy, et cetera. But it is like a code because it's about moisture management and durability and so many more sort of, things besides just energy use. But quickly, my background, I actually started my architecture career in Telluride before I had an architect. I was a physics major as an undergrad, went to school back east, and I just wanted to live in Colorado. So I had taken an architecture course and was able to get a job as an architect in Telluride and started doing high-end custom homes in the mountains. And that was amazingly fun, loved those projects, but it also was a little less fulfilling in terms of what I'm giving back to the world. It was like doing these super huge mansions is not sustainable, no matter how sustainable you say you're making them. And what we were doing in reality was not, it just wasn't making a difference in my mind in terms of what we need to be doing. And I also wanted to give back more culturally, so I went back to grad school for architecture in New York and worked for a few firms there that, mostly in the higher education and civic, museum, library, those kind of projects. And then moved up to Boston where my wife was in grad school. She went, got a second master's in landscape architecture, and while we were there, I worked for a firm also doing schools, and so sort of bigger projects, not very sustainably focused, but very, I would say my first firm in New York was FX Fowle. They were like known as a sustainable architect in the early days of sustainability, the first LEED platinum building in New York. And, mostly our focus was on social issues, which was also very fun to me. But then, when we were moving out to Denver, I as I said before, wanted to join with Morgan to rekindle my Passive House, or put my Passive House training to use. And it is something I'm really passionate about. And I feel like something that when people understand, people kind of realize that it really is the way to make, you don't have to certify Passive House, but to use this sort of building science, it's very fundamental, simple, and makes such a huge, actual difference in terms of energy use. So we have to do that. So this is actually the cover slide to a lecture I gave with a colleague at Emu Systems, they do Passive House consulting, not architects, but they are trained architects. And it was for the AAA last year, and it was really about resilience and durability, not really about energy. So that's just something to keep in mind. I'm going to talk about the energy use, but that it's such a sort of bigger picture. And when it comes to sustainability, like durability of buildings is a sustainability tenet. You're not going to have to replace it and not have to replace parts. So Shape Architecture is Morgan and Morgan is remote in Washington now, and he does have another job. So it's basically more me, but he's hopefully going to come back. And we do have 2 employees and, a lot of active work. This is a little bit out of date, but I'm also lead AP. And, we have, actually we're up to 7 now, Passive House projects going. And where's the, so this is just sort of showing a smattering of our building types. So there's, some of our past projects between Morgan and I at the schools, and but then we also have going a hotel project in Gunnison, which is climate zone 7, coldest climate in the continental US, and it's on track maybe to be the first Passive House certified hotel in the US, 18 room or so downtown. And then, down to tiny ADUs, which is also very sustainable, right? You're increasing density with the least possible material. Projects all over the state, we're showing some of the, and then as well as we've got a project in Georgia, a multifamily Passive House going there, and up in Washington. So segue suddenly to what we all came here for. So Passive House is something that again, it's a sort of building code, and this is the device that in theory you can use to heat your house. That's the entire amount of energy it would take for approximately 1,500 square foot house, a little small, depending on the climate, not in Gunnison, potentially in Denver, but potentially you would need more than that in Denver. So that's just an image for your mind. And it's a voluntary standard. I kind of talked about this. 90% energy savings compared to a typical building stock is like buildings built in the 70s. 75% is compared to code, but it's not actually depending on the code that's adopted. So the codes are making huge improvements. You know, we're already at IEC 2018, which is better by little than 2015, but 2012 was a pretty big jump. So code is getting there. You can kind of see on this chart that like an average existing home uses, you know, this many BTUs per square foot. The passive houses down here pretty darn close to zero, and it's the best way to get to net zero, you know, just a few solar panels. But you know, we're at least halfway there just by meeting code, which is great. There are other issues with code that need to catch up, and then halfway is still not far enough. And so just like the basic reasons why this is a good approach is the energy use, which is talked about, sure. Number two, though, is the occupant comfort. The really good wall assemblies and really, really good windows mean that you never have what's called, you don't have local temperature differences. You don't have what's called radiant asymmetry, which is like the leading cause of occupant discomfort. If it's, you know, besides temperature, you end up having like really, really stable temperatures. So if you're near a window like I am right now, that window next to me is literally 20 degrees. A code window on a day like this would actually be in the 50s in terms of degrees. And then you might have a heater going that's going to be much hotter than the temperature you want on a different side of you, or, you know, or the air to ambient temperature. And just because one side of your body doesn't feel the same as the other, it makes you feel uncomfortable. It means you have a much narrower range of comfort to feel, you know, to continue to feel comfortable. And the other thing that happens there is you end up getting like a downdraft off of a window if the window is cold, because the cold air drops, and then you end up with getting like a convection loop in a room. It feels like a draft, even if it's not a draft. And even additionally, actually probably have drafts in a typical building, and that's not something that's addressed very well in code right now. So a passive house window, in order to be certified, there's like a comfort criterion in the standard that means that so typically in our climate zone you need a triple pane window. The interior surface would be in the high 60s. So if you have a 68 or 70 degree room and your window surface is 66 on a 0 degree day, you're going to feel really comfortable. That's a picture of these kids like sitting, touching the window, no frost on the windows. And then the other component is you have to have continuous fresh air mechanical system in all passive house buildings. So typical ventilation systems, you might have like none in a house. If you have something, it might be cyclical, like you turn on a bathroom fan or you turn on your range hood and maybe there's some intake air to make up for that, or if you have a fireplace. But the continuous nature of it means that it's very, very, very slow. So you don't hear it, you don't feel it. There's no like feeling of air movement, but it does end up moving air all the way around the house. And you use what's called an energy recovery ventilator or heat recovery ventilator. It's slightly different, but the principle is the incoming air passes through like a series of straws on its way in. The outgoing air goes past it and gives its heat. Up to 90% of the heat energy in the outgoing air is transferred to the incoming air. And so it's like basically you're not wasting any energy with your mechanical system, which a typical mechanical system basically throws away all the hot air that's already in the house and brings in cold air and then heats it. So that's super efficient. And then because it's constant, the air quality, and it's highly filtered, air quality is like perfect all the time, which is another source of occupant discomfort. And then the energy recovery ventilator also balances for humidity. So it's typically more humid inside than outside in Colorado. So that becomes balanced, and you maintain the humidity much better, which is another source of occupant comfort. And then lastly on this list is acoustics. So really good windows, really thick walls, really good air tightness. it's a quiet environment. And if you're near a road, like my office now, it's much more pleasant. And then this number 3 is, so number 2 is really maybe the most important reason people should build to a better quality, whether or not it's certified passive house, but thinking about it. But the durability is a really, really big thing. And right now, code is in a bad place because there is a requirement for air tightness, but there's not a requirement for for ventilation. And then there's also, there's a requirement for a class 1 or 2 vapor retarder on the interior of your wall assembly, which means it'll keep moisture out of the wall in theory. But they're never built very well. There's no inspections on how well that's applied. And if water does get in, vapor gets into the wall, it will not be able to get back out. And so you end up with a ton of condensation risk. Basically all buildings built right now are gonna have mold issues in who knows how many years, 10 to 20. The other issue is thermal bridging, which we'll talk about. But if you have, like in this case, there's steel studs in the wall that you can see there, and they're bringing cold in from the outside. And when the moist vapor that hits those cold studs will condensate, because you guys are scientists, as the air can only hold a certain amount of moisture, a lower amount of moisture at lower temperatures. So it'll condensate on the cold surfaces and turn into water, which is what causes mold. It's not so much the vapor. So the durability is a huge thing from just the good building science and thinking carefully about the layers. And that is part of becoming passive house certified. It's sort of like a part of the review. And then also just something where sort of like, once you're trained, you think about naturally. And is part of working really closely with the contractors. And then the last point here on like why it's a good system as contrasted with some other systems. I mean, something like LEED can cost as much as it needs to. Like it could be ridiculously expensive depending on the complexity of the systems you put in, or it could be fairly cost effective. It's sort of undetermined. With passive house, the idea is you spend all your money on the envelope and you take it out of mechanical systems. And so in Germany, where it was sort of originated, you can take out the mechanical systems almost completely, with the exception of the ERV, and the savings there really do close to balance out with your additional costs of your envelope. And then the other thing is, so here it's a little less close to equal, but in terms of long-term, because the durability is so much better and the mechanical systems get smaller and simpler, the maintenance goes down a lot. And so you end up with long-term savings. And so at certain scales, it's sort of a no-brainer for large buildings that have large capital maintenance costs over a long period of time, and they're long-term owners, like say a school, that is going to pay off pretty quickly, or at least over the time that they're going to be spending money on it. So pretty simple diagram, I say 0 to 7% initial cost increase. 0% was something that they got to in, I think the Pittsburgh Housing Authority has mandated all new affordable housing, city-built housing is passive house. And they figured out, basically, it probably ways to value engineer that made it cost neutral with the way they were building before. And then when it comes down to long-term costs, it's like, there's no reason they would never, ever go back. Having said that, we've found, I'll talk later about different assemblies. If you do, like, one good way to do the walls, do double studs. So right there, you've doubled your framing costs. And right now, lumber is extremely expensive. So it's doubled in the last 3 or 4 months. So the cost neutrality is like a very hard thing to quantify. And everybody always asks, you can't put an easy finger on it. Quick history, try to be super quick. But this is 2 pictures of what it is and what it is not. So the picture on the left is not a passive house. That is a passive solar house that was in, and there's in the 60s and 70s and 80s in the US, there was like a ton of proliferation of attempts at sustainable building. A lot of really great ideas, but the science didn't really work out that great for a lot of them. There's one reason that it's not more popular now. And because the name passive house is problematic because people associate it with, like, this is an earthship, or like a lot of, things like trom walls or thermal mass in the floors. They're great ideas, but end up sort of just the energy savings associated with these kind of good ideas goes away if you don't have an air type envelope, right? The air just leaks out, takes the heat with it. So all those, like, I mean, they can be really comfortable and awesome. No slight, but the picture on the right is actually a house that was built in Alberta in the 70s, and it has R40 walls, which is kind of like the target for a passive house in that climate now, and an R60 roof. Likewise, we're doing that all the time. And they spend $11 a year to heat that in Saskatchewan. So the ideas were there in the 70s. And actually so North America was actually like the pioneering place where this stuff was figured out. A lot of things on the left were built, but also some things like this house on the right. And then these like German building scientists caught onto this and kind of quantified it, and created the passive house standard in the early 90s. And then, so this was the first passive house here on the left. It's kind of ugly, but it's actually performing exactly now today as it was when it was built. They've got monitors in the walls, no decline in performance, and it's exceeding the passive house standard, and it's built with super simply. So, and then obviously this picture on the right is just to show it can look pretty awesome too. It doesn't have to look like a box, but that was the initial attempt at it. And so it kind of went to Germany and has come back. And I just showed this slide, if any of you are ever going to be involved in the building field, you don't want to do houses, passive house buildings can be anything. The building on the top right is the Portland Friends School in Morgan, who started shape architecture, and Junko introduced, actually was the project architect on that. He had a large part in designing it, and was also really central on the team that did the energy modeling for passive house. And so, and that was just like such a success story of why it should be incorporated, and super happy client. I'd like to pause. Any questions so far? If no one answers, I'll charge right ahead with the actual science. So there's 5 principles, 5, not 10. And here they are in German, but there's like a little subtitle in English. So the obvious first easy thing everyone would guess is insulation. You need a lot. Then the passive house windows is the second thing shown here, and that's tied in with, it's not just good windows, but it's the solar orientation. So you want to have like 50% of windows south. You want to have a long axis facing south, so kind of like basic green building notions you've probably already learned about. But the windows on a passive house become part of the heating system. So you're actually gaining more heat in the winter months when you want, in the heating season, than you're losing, and by a pretty good factor. And so they become at least equal source of energy of your internal energies, heating system. But that means they have to be oriented right, and you have to have enough of them facing the right directions, and really, really good quality. And that is the place that the biggest expense on a passive house. But then they also have to not leak energy as well. So you want to have typically a high solar heat gain coefficient, SHGC. Most contemporary windows, the common knowledge is that they should actually have low solar heat gain coefficients, so you don't overheat. And obviously that is relative to the size of the building and the program and the internal ones, et cetera, but rule of thumb. Next one on here is the ventilation, continuous fresh air, which we talked about with heat recovery. And then air tightness. Air tightness is actually like the biggest thing in terms of making a difference between code and, like if you could do one thing, it would be air tightness coupled with heat recovery, because you don't want to overdo the air tightness unless you can get that energy recovery ventilator in there. But that's the thing that makes the biggest difference for the least dollars, for the least labor, for the least space. So we're doing high performance duplex here in Denver. All we're doing is an ERV and air tightness and code insulation, but it's still going to perform much better than the next. And we have some analysis to show that. And then the last thing, thermal free bridge free construction, is kind of where we get to do anything as architects besides add insulation to the walls. Is we have to think through all the places where, like, if you have a balcony, how is that going to attach? You can't just cantilever that, because every piece of steel that runs from inside to outside is going to be a problem. So we'll get into that a little more. So that first point, the higher value continuous insulation, kind of showing on here what the walls, roof, slab would be. And then just, that point that I guess this sort of dips into the thermal bridge conversation, but like a steel stud means you don't have continuous insulation. I think you do. That needs to be outside of the studs, or you could have a double stud wall, for instance, and the continuous insulation is between the studs. You know, it just has to not be broken. And then you have to think about that all the way around. So it's not just like this wall's got it and the roof's got it. How's it connecting from the roof to the wall? How's the window aligning with the insulation so that we don't have like a little place where, you know, heat sneaks in or cool sneaks in. And then the other part of that is the comfortable interior surface temperatures. So it's not just, I mean, there's the durability that is associated, and obviously energy savings, but then comfort. And then that air seal, as I was talking about. So the passive house level is 0.6 ACH50. So that means 0.6 air changes per hour. So the volume of the house times 0.6 is the amount of air that can leak through the walls. That actually sounds like a ton of air. But that's when it's pressurized to 50 pascals, which I can't really give you an analogy for 50 pascals, but if you pop up the house with a blower door, that's just a picture of that, you know, these fans blow it in, crank it up to the target pressure, and then it will leak out at that rate. A code right now, which is fairly new, if you know, jurisdictions that have adopted the 2015 energy code allow up to 3 air changes per hour. So we're at 20% of code. But a standard house, like my office actually you wouldn't be able to pressurize. It's just like infinite air changes per hour. But like a standard house might be 7 to 10, you know, air changes per hour. So getting down to 10% of what this current construction, 20% of current code construction. So that's like where we're really the biggest difference. And then, you know, there's so many repercussions to that. It has to do with durability. Drafts is like the biggest thing in terms of thermal comfort. Moisture damages, so huge. If you have a tiny leak into your vapor barrier, air barrier, you're gonna have a ton of moisture. It's not just like the percentage of wall area that has the hole in it that the leak can go through. That will actually be like a funnel. So it'll actually draw more vapor in, and then obviously reducing heat loss. And again, the effectiveness of the insulation is only as much as the air tightness. So if you have like bad insulation in a stud wall and they're like a little wrinkled between the bat and the wall and the stud, air that could get in there will convect from the interior to the exterior and bring that heat energy with it. And sort of, it's not just about that, like quantifying that gap. It's also keeping in mind that there's an additional form of heat transfer that will occur. And then the thermal bridges is, you know, a thermal bridge is actually technically like any corner. So, you know, the bottom, where like everywhere, you actually have to quantify all of the corner conditions. But where it's really a big deal is like balconies, you know, or steel or structure that would go from inside to outside. You know, this example is a little tired because everybody shows it, but the Aqua building in Chicago, which is like pretty cool architecturally, cheesy, but cool. It's every single one of those balconies is just a continuous slab that goes from inside to outside. So it's literally a radiator, like the definition of a radiator that is heating the air in Chicago. It's just heating the air in Chicago around it. Like it's, and there's no way to mitigate it. So I've seen Gina Gang talk about this. She designed in these thermal bridge isolators that are like basically structural insulation foam. This like kind of like have all these rebars that are come from both sides into this like composite that's non-bridging, but it's super expensive. So the builder was obviously like, no. So since then, Jeannie's like, I will only design things that take into account in a non-value engineerable way, you know. So she did another really cool building where they've got a whole superstructure on the outside for balconies. But you know, there's also like if you had a steel beam to make it look cool that goes from inside to outside, one steel beam penetrating the envelope has 5,000 times the conductance of the passive house limit of all the thermal bridges. So you just can't do it. You have to like, you know, and that's like the most extreme example that's kind of predictable, but you know, everything we have to be careful about, you know, eaves are the biggest challenge, how we handle just like structure going from inside to outside to carry roofs. High performance glazing, I talked about a little too much earlier, because there's not that much to say here, but I guess it's to think about the actual construction of the window. The losses, it's easy to think, okay, triple pane, cool. The triple pane works really well. The R value there is very high, U value is very low. But the frame is actually harder to deal with, especially on operable windows. So they need to be thermally broken if possible. A lot of times they'll be, I mean, I hate PVC windows. It's like the cheap, crappy thing. But PVC is actually a really good or a really bad conductor. So really good at isolating. So you don't necessarily need thermally broken if it's the whole thing is made out of UPVC. But a timber window with aluminum clad like this is more beautiful. So you see in this image on the lower left how it's constructed as that foam between the wood and the aluminum. And then the spacer bars, like you have the 3 panes, you have to have something to hold them apart. That has to be low conductivity. And that's like a huge source of sort of thermal bridging in windows. So that's something where the cost escalates pretty quickly for a passive house level window. And that's what stops projects the most often. And what's tough right now is it's hard to find a good window that's like there's like the passive house level A, passive house level B, passive house level C windows that are good for different climate zones that meet the criteria depending on how challenging the climate is. There's no like comparable that I know of a passive house level D window. Like it's just the next thing down is kind of, all right, we have a challenge with that. And then the ERV, this is a kind of a diagram that I showed, how the air passes, what I mentioned, the warm and cool air kind of pass each other. And it's kind of amazing. You'd think that like you could only get like half of the heat from the outgoing air, but you can get up to 90%. And that's one thing that's like mandated by the Passive House Institute is to make sure that your ERV is efficient enough. It just has to be super high efficiency. And then there's, besides the fresh filtered air and the lack of thermal losses, there's the humidity stability is a really huge bonus of that. And then this image is sort of related to the window thing. The passive solar should be 1/3 of the heat gains, and another 1/3, and this is during the heating season, which is dominant most of the places that we do work. The internal gains, just people, bodies, the computers, the water heater, the other stuff in the inside of the envelope are going to be 1/3 of the energy. So that's if you think about like the quantity of that, just a few people and like a little bit of sort of low grade equipment adds up to as much energy as the last portion, the heater. So pretty low loads. And this would be, in a traditional building, the heater would be at least 2/3 of the pie, and the windows would be very, very little of it. And this is factored for their losses. So the level, at 4.75 kilobtu per square foot per year is, I guess just to mention about the metric, to hit the standard, you have to show that you're hitting these metrics. You can actually either certify based on your load or your demand. So you probably know the difference, but the difference is that the demand is the total heat used over the course of a year, and so the energy used to produce the heat that you put into your building over the course of the year. The load is the peak. So on the coldest day of the winter, and it's like, there's the rule for it is sort of like averaged over the coldest 24 hours, I think, of the year, the heating season. In Colorado, it's impossible to use that as a metric. You just can't. It's gonna be cold on the coldest day, way beyond what you could heat with this much energy. So, or to compensate for the coldness. The demand is, so always what we go with, is the standard was established in Germany where it never gets that cold, but you also have way less sun. So in Colorado, it's actually a pretty great climate for passive house because we gain over the course of the year, we gain so much solar energy that pie chart is actually really easy to hit. And it's maybe a little more challenging in Germany where the standard was developed, but the heating load is a viable way to calculate it. And I'll talk a little bit more in a little bit about why there's those two options. But then cooling has this asterisk, so you don't really, it doesn't come up here in Colorado. And you know, we do work around the country. The only place that it's been an issue is in Georgia. We have this project in Georgia, and even there, it's actually a heating climate slightly, but the heating is slightly more demand over the course of the year than the cooling. And so even there, cooling, and that's factored for humidity. So it's a latent. What's the other thing? So it's not. It's anyway. So if you have to add additional energy to compensate for humidity that's allowed, which they kind of have to do, or you wouldn't be able to do passive house in southern regions. But then the primary source energy, this is again, in houses doesn't really factor in, you know, always works if it works for the heating, but in, you know, larger buildings where you have a lot more internal loads, this would be the driver. And it's the primary source energy demand, which is not like how much energy, you know, in your electrical meter goes. It's actually factored, you have to factor it by the losses in the system from when the energy was generated. So if you have an electric house that's off grid, you don't have to factor for that. There's just a little losses in your transformers, but the grid is pretty dirty in the United States. You have coal, there's like trucking, you know, train moving the coal around and trucks. There's like the transmission losses in the power grid, which are quite high. There's like losses of efficiency from the fact that the power, you know, generation plants run 24 hours. So that's factored in, it's like a factor greater than 3. So whatever you use in the house, apply that by 3.3, I think, or it's different in different regions. That's 38 kilobtu's per square foot per year. Because the metric's kind of hard to really relate to that, but it is a pretty low number compared to typical, you know, but I mean, again, now that there's like LED lighting all the time anyway, we don't really have to try very hard on this primary source energy metric, but if for bigger buildings, it takes a lot more attention. And then air tightness, we talked about with 4.6 ACH50. And then this last one, excess temperature frequency, that just has to do with thermal comfort. So you can't have a window, so there's like a temperature range, 68 to 77, I think. And if anywhere in the house, you would not be within that temperature range for more than 10% of, I forget, you know, it's like not 10% of the year, but that window has to meet that comfort criteria, like not exceed, not get outside, not allow the temperature inside of the room to get outside of that range for more than 10% of the time over a certain hourly period. So that's like the one sort of more qualitative criteria, and that's it. Those were all the things for passive house to hit the metric. And then just a couple of interesting things about why. So the idea here with the heating load was that in a favorable climate, which Colorado is not quite, but basically if you keep under the 3.17 BTUs per square foot per year, you don't need a heating system. You actually can just put a little electric resistant heater, as you see in this diagram, on your ERV for the intake air, and it will be enough to keep your house warm within that temperature frequency criteria all year round. And so that means you just got rid of like your boiler, your in-floor heat tubes, you got rid of your furnace and the ducting and everything associated with it. And it's just like a little electric resistance, which electric resistance is horribly inefficient, but it's that diagram of the hair dryer, right? Like if you could just get rid of everything and only have a hair dryer, and then think about maintenance and durability, et cetera. Unfortunately, in Colorado, that doesn't work. We just have colder days. So you'd still need more horsepower to just be there for when it's that cold. But that's why that number came up. But then the 4.75 is a little more, it may, you know, that's what we are always aiming for. That's the 4.75 kilobtu's per square foot per year. And that's the idea there in the way that the standard was designed is that if this is a graph, this blue line is the amount of energy, your dollars you spend on energy. And that's going to increase linearly depending on, or decrease linearly depending on how good your envelope is, right? So the less energy your house needs to use, the less you will spend on it. Linear, right? It's like increase your R value, you get that much less energy used. But the costs you put in are a little bit exponential, right? You like go from a code building down to like, okay, maybe you add some insulation. That's pretty cheap, but you add more insulation, all of a sudden you had to go to a double stud wall, little cost bump, go to 6 inches of exterior rigid insulation. That means your fasteners increase, or you maybe need a shelf to hold your siding. Costs go up, windows, costs go up. You know, down here in the ultra low energy building realm, you're pretty close to passive house, but you're not there yet until you get to this like tipping point where you can drop out mechanical systems. And again, that tends, in my experience in Colorado, now that I'm doing passive houses and certifying them, that's more theoretical than real. We are having challenges with mechanical systems because, I mean, often like the best thing is using mini split systems, which can use, there's definitely savings, but it's not this like theoretical get rid of the equipment, to be honest. But this is sort of like where why that number is that number. Once you hit that, drop out mechanical systems, reduce the cost a lot, and then you hit the sweet spot where you can continue to get even more higher performance, but then you're paying more and your overall cost goes up. But this like total cost of the actual heating cost plus the cost of the building, there's that sweet spot. And again, so climate related. And then that 38 kilobituses per square foot per year of energy, total energy use, comes from this macro problem we have that we're facing with our species and our planet, that I really believe in, you know, and we're really, this graph was created before we left the Paris Climate Accord. So it's really scary. You know, we're heading into this very red zone of like, what's going to happen to our species and all the other species, right? Like nothing good. It's not looking good. And if everyone on the planet built or met the passive house standard with their life, which, you know, in a lot of places, people are way, way under the BTUs per year for their lives living, you know, in whatever conditions in whatever countries. You know, if you live in a hut, you don't have any energy use. And there's a lot of people in the world living to much below the passive house level. But we in North America and in Europe are just like, you know, eons above it. It's terrible. So if we in North America could like all hit the passive house standards, and this is like, you know, Joe Biden's climate plan, right? Like if we all do, this is the buildings portion of it. We have to do this to get the energy down. You have to do the building science. You know, then we could stay below that where's the number? The 2 degree Celsius global temperature increase. And again, this graph is from 3 or 4 years ago. So I don't even know what's happening now, but the metric stays the same. But that is where that total energy use came from in the sort of just thinking macro. And it's achievable and it's very necessary. So pausing again, any sort of like questions on the standard science? Pretty simple. So yeah, what I love about passive house is it is really simple. You know, that I keep talking about building science. It's like when you get into the moisture management stuff, it's really a little bit, you have to know what you're doing. And then there's a lot of like really great collaboration that has to happen with contractors because they're in charge of it, right? Like if they put a hole in the air barrier, then the whole thing is sunk. So there's education and there's like, you know, the right contractors, so the contractors that aren't that into it, and you're like, this is going to be passive house, they're going to be like, that's not worth it. Because energy costs are low, it's probably not worth it. But if you're thinking short term, and then they want to make a buck, they don't want to like put the extra, it takes a ton of extra time for them. It's not really that much materials necessarily, but they need to really pay attention. But you get a contractor that's interested and that wants to make a difference, they have so much power with passive house, right? They're not like tracking down lead like product declarations, you know, and having to do a bunch of paperwork. There's no paperwork. They just have to really pay attention and do good quality construction and like, you know, be testing the air tightness on a more ongoing basis and like thinking ahead about like, okay, we're gonna have to wrap a smart vapor barrier, air barrier around this like junction in order to keep air from sneaking through there. And then like thinking about it and and then if they're a contractor that's interested, then they love it, right? Because they're in control. Whereas, you know, with something else, it's just paperwork. So that's kind of cool. So to address what's on the screen now, one thing that's sort of weird about it is that as a standard, you know, not the building science, but the principles, but the smaller the building, the harder it is to achieve because the surface to volume ratio is worse. So we're doing a project in Crested Butte right now it's an ADU. It's 1,200 square feet plus a garage. It's 1,600. And the passive house consultant who's doing the energy modeling has said that we can't achieve passive house. It's basically not possible because it's in climate zone 7, which is the coldest again in the US. And for a lot of really important reasons, it's not ideally oriented. And then and then the size just makes it like we could be in that climate with that orientation and be, you know, twice as big. If you had twice the floor area, you would have whatever, I guess just twice the air volume, but you would not have twice the envelope area, right? So you have way less heat losses through your envelope. And that's what's demonstrated here. So this is our, you know, 2,500 square foot passive house in Littleton. That's going to start break ground any day now, presuming they can get through the snow. And then the hotel that's in design, and sort of we'll see when it gets going, but that's 14,500 square feet and 18 room. And even though it's in climate zone 7, it was way crazier than Denver, you know, Littleton, which is like a really easy climate to hit it. It's a much smaller wall assembly because the 18 rooms, if you think about each room kind of as a house, they only have one facade, right? So all the other walls of that occupied space are adjoining other heated parts of the building. So you only have a fifth of the losses in a way from that. And so the bigger you get, the more true that becomes. You have 45 unit affordable housing in Maine, which is a tougher climate than Denver, not as tough as Crested Butte, or Gunnison, but pretty tough. And this was achieved fairly not cost neutrally, but this was another project Morgan worked on in Portland, Maine, and they won a bunch of awards for affordable housing that they used passive house approach, but it wasn't like, that didn't necessarily factor into the awards as much as that the heating costs for the tenants or for the owners is so low. And, you know, but the construction system wasn't that onerous or expensive or complicated. There were some details that required a lot more attention and some things that people weren't done the standard way. But just again, the size matters, and it's a little unfortunate because it encourages bigger houses, right? Like the clients I have in Crested Butte were like, well, maybe we should make this bigger. I was like, no. We're trying to like reduce energy here. You're going to use more energy if you do that. Like, don't try to hit the standard. But it is, so there's that, which is a negative thing, but it also is like, it only makes sense to do it on a square foot basis because you just can't hit the same numbers with a bigger house. So, you know, another thing too is like you can do it any way you want. This is a very, very contemporary house we're working on right now that's in the permitting phase and up in Boulder Canyon. And, you know, it's going to have like the most expensive windows you can buy, and they're magnificent, just so beautiful. It's lift and slide doors, huge expanses of glass, which is great. They're oriented perfectly. And good overhangs, so you know you get good shading in the summer, won't be overheated. But the you know the details we had to go through to create these. It's a pretty simple concept, like 2 stacked, you know, rectangular shoe boxes that are just rotated 8 degrees relative to each other. It's just the same number of degrees that the true north is rotated from solar north. And but to, you know, to achieve that, we have like a lot of really complicated, you know, we're trying to have a flush threshold. So where we do, you know, we're adding a little bit of insulation between the, you know, the blocking below the doors and holding back the slab. And then we have this cantilever. So we need to like wrap the exterior insulation extra around in the back. And then, you know, we have this like complicated way that we're supporting the ledger to support the deck that's also concrete. So like, this would be pretty easy. Well, it would never be easy. This house would never be easy to build. But if you weren't doing passive house, you wouldn't have like, here we have a beam. We have a beam, I guess, shoot, it's not really okay, so we have a beam right down here over the door, and then another beam out at the other end of the lower roof, then another beam at the other end of the upper roof, and then another beam that's outside of the insulation. It says there's a steel beam here that's a little hard to see, that's, you know, supporting the back edge of this deck. So it's like thermally broken. So there's no steel that goes interior to exterior, but boy, it was hard to figure out, you know. And there's like this corner over here, there's like a steel beam that goes into the, over the mudroom. So we had to create that thermal envelope, like going down underneath that steel beam. So you can do that, and then it costs a lot. Or you can do like this house that I showed earlier. It's really just a double stud wall, and it looks like any other construction. You know, you're stacking a double studded wall on this regular footing. We're not insulating around the footing because we're providing a thermal break between the basement slab and the footing, and then we have the double stud wall. It's thick enough to just kind of like cover everything. So it's pretty, you know, that's the that's the other way to do it. And then twice as many studs, actually, as of 6 months ago, was not adding that much cost. You know, you got the framers on site. It increases their cost, but the framing is not like, you know, hugely impacting the overall. This project is coming in at like $167 a square foot, which is the lowest we're doing in the Denver area. I don't even know how I don't know how they're doing it. Like the contractor definitely wants to do passive house, so they're cutting all the breaks they can. Having said that, I think there was recently like a $40,000 bust because the lumber prices doubled, and it's a double stud wall. So if we'd known that was coming, we might have done a different wall assembly that had like exterior insulation whose prices are more stable right now. But again, that complicated versus simple thing. And then, you know, we just to show off a little bit of this Gunnison Hotel. It's going to be the tricky part on this one is the sort of ventilation requirements for the commercial spaces on the first floor, and then the like doors. We don't have we really didn't have a good way to do airlocks. So that is a best practice. We should be doing airlocks, you know, having like a door into a vestibule into another door, and we don't. So this is going to be really challenging. And this we're like pushing the envelope. Whereas upstairs we have, you know, just like the rooms, really great windows, really good form factor. It's like the perfect shape, right? It's like slightly elongated in the east-west, but because it's sort of square, it's like the best form factor you could have for the building this size. And then, you know, mix the rooms, and then, but this is just like, so showing how we did the analysis on it. This is a slide that I developed in conjunction with EMU Systems, who I gave that lecture with at the AAA before. So I'm a little bit stealing from them. I don't think they'll mind, but they, we don't do the energy modeling because we don't have time. We're designing a lot of buildings, and so it's better to outsource that to the real experts, right? But I was trained in PHPP, which is the energy modeling software, and I would encourage all of you to do it yourselves. But these guys are really, really awesome, and so they took our ArchiCAD model and then brought it into SketchUp and created this like very simple SketchUp model that analyzed the heat on, or the solar energy radiation on each window, depending on, you know, orientation. And then they did an analysis of sort of like what windows are necessary. Like we have these 5 options of windows, which are like at different levels of passive house, like performance, or not passive, but just performance, you know, U values, window U values, spacer U values, whole unit U values. And then what if we do, you know, in each HRV that doesn't recover, does not recover the sort of managed moisture, but it does a slightly higher, more efficient job of recovering heat, but not energy. So sort of comparing, what if we did this, what if we did that? And it was like, you know, then the third thing on this matrix is like, what's the R value of the walls? And so you can kind of come up with and you kind of want the sweet spot to be like, where is it going to cost the least? We don't want to do better than the standard because it's going to raise, if the cost is going to start to spiral. So we want to like hit that sweet spot of like, well, it's probably worth doing the medium R values because we're not exceeding the standard. It's going to be more buildable. We're not going to use special fasteners for insulation, stuff like that. But then also we're, it means that we can use the like medium level window. So it sort of like quantifies how to make decisions when there's all these different variables, like what air tightness is going to be, which window product, which orientation, you know, solar heat gain coefficient. Is it going to be high solar gain, low solar gain? This kind of can run the energy model to show, well, it should be low solar gain in the west and high on the south and east, or something.
We're basically
and then
out
also,
of time, Steve. So
okay.
we're basically out of time. I don't know if you have a few sort of last things that you'd like to wrap up with.
I think I can basically stop with that, and I think it'd be good to hear if anybody has any questions. And I could talk for hours, but I think that I gave you the gist of the important, you know, the important points. So, yeah, is there anything that was confusing or I could use more clarification?
Well, I guess I do have a question, and you know, people can stick around, I guess, if you know, since we passed. But I was thank you, Steve. First, I thought this was really interesting, and I appreciate you taking the time to chat with us. And I am curious how or what you need to do for like indoor air quality, because I know indoor air is often, you know, more polluted, dirtier, whatever than outdoor air, and then as you lower your air exchange rate, you're increasing whatever those concentrations in a house might be. I'm curious, you know, how you address that, or if maybe that's not even an issue, and I'm just like overthinking it or whatever. But I'm curious, like, how you sort of balance the air exchange rate with the human health, you know, implications of lowering that air exchange.
Yeah. You cut out a little bit at the end, but I think I got the gist. But basically, you would have a separate system for your range hood. So that's really important because that's the biggest source of indoor pollutants. But then we typically don't do a separate system for bathroom ventilation. And then the low ventilation rate actually works out over the course of, you know, because it's continuous, you never really accumulate like the pollutants from whatever is happening inside the house, except for the cooking, right? So typically having a separate range hood, and then you do need to have separate intake air because the ERV system has to be internally balanced. You can't rely on the ERV system to, you know, increase the intake air because you have this other exit, you know, source of outgoing air. And typically the range hoods, they're on for such a short period of time that you don't need energy recovery ventilation because it's not continuous. So we will, if things are looking good with the energy model overall, and there's a little bit of wiggle room to spare there with the overall heating demand, you'll just use a typical range hood with a typical intake, and you just want to have a really good damper on the exhaust and intake air, you know, of the range hood. You want those to be interlocked so that you never have any leakage. And then really the quality of indoor air is exceptional, unless again you had some, like if you have like a paint booth in your house, you'd probably want to ventilate that separately. But you know, I think the other question with that related to that could have to do with construction materials or like, you know, formaldehyde used in the interior furniture products. And I don't have a good answer for that. I think with a typical like code compliant low VOC paint, that's you know, it doesn't remain an issue. The continuous ventilation again just takes care of it, and it does tend to be really high quality. But yeah, whether you need to use another fan source for a whole building flush out before you know, let people move in because of things like formaldehyde and furniture. That's a question I don't know the answer to. But
there was a related question asking if with COVID, if that has affected any of the sort of air exchange rates that are desired.
Well, no, we haven't had that come up. Basically, all our current certified projects are houses, with the exception of we do have one that's a multifamily building, but still those are sort of like independent housing units, and the ERVs are not mixed, right? So your outgoing air, I should say that again, like that we have a 14 unit building, with 3 ERVs. So obviously they're serving multiple units, but the outgoing air does not mix with the incoming air. So no incoming air, outgoing exhaust air from each unit mixes with anybody else's outgoing air. And that is something that's different from some other, large ventilation systems. But it's extremely safe with regard to that. And we feel like this hotel project, it's a selling point. And the other one that is a current event is the fires. So smoke, it's actually very easy. The filters in the ERV systems that come with them are very good, but you can increase the quality of those filters, replace them with a HEPA filter or add a HEPA filter so that they really do have a huge impact on indoor air quality. And then the fact that they're continuous really takes away the potential for leakage, which, the worst thing in buildings is when you don't have continuous ventilation, you have all the air you were breathing is sneaking in under the wall, through the joints. And that means you're getting the smoke from the wildfire in addition to the, mold that might be in your wall. So yeah, the Passive House being really airtight is a great fit for today's air quality. Looks like we lost Junko.
I have a quick question.
Yeah.
In terms of, I guess, going off the air and whatnot, are there different types of buildings that are not feasible for Passive House, such as a laboratory building on a university campus, or just certain very energy intense building? Is there a limit to which Passive House that they're exploring, trying to make these buildings Passive House, but maybe just the nature of what is needed in the building doesn't allow it at this moment?
No, that's a great question. And I think that I don't really know. I mean, in Europe, they're doing hospital. A hospital is one of the highest energy intensive kind of buildings there is. And I believe there have been Passive House hospitals, at least underway in Europe, but not in the US. And I think partly it probably has to do with the fact that our climate is more challenging. So we have less wiggle room to make up for, that extra. You would have I think a lot of it is the ventilation systems that just not only take energy, but also are a source of loss of energy through, taking air out of buildings. So, the schools have been done here, and office buildings for sure. It's not a big deal. The high occupancy stuff where you have a lot of ventilation requirements is where it gets challenging. And then, where you have a lot of coming and going, like our hotel first floor makes me nervous, but the immune systems is okay with it. But no, it's, I think it would not be a good fit for your parking garage. Unfortunately, you can't get really good garage doors, and then you don't want an interior environment for your parking garage. So, yeah, I don't know the answer all the way through, but more than you think can be done.
Okay, that makes sense. Thank you.
Yeah, it looks like people are. Any other questions, or should we let people go? I'm happy to field any other questions.
I have a question for you.
Yeah.
Was it tough for you to transfer from being a physicist to getting a master's in architecture? Because I'm honestly really thinking about that track and maybe architectural engineering instead, maybe to be more on the structural side. But how hard was that for you? Did you have to take a lot of prereqs because you didn't have a background in architecture?
No, it was easy. It was great. Well, actually, I take that back. So I was lucky because I had taken 2 classes in architecture as an undergrad, and then I worked as an architect. I was just super lucky to be able to get this job. I don't know what stars aligned. So I was able to skip. There would have been a requirement for summer intensive, which is really, I highly encourage if you're considering it. So a lot of schools offer it. I went to Parsons, the new school in New York. I don't know if Boulder has one. It's summer, an intensive pre-architecture program that you can take. But I would recommend doing it because it throws you in the deep end. You just kind of like practice. You do the things that you do in architecture school, and you find out like, this is actually terrible. I don't want to do it. And I was able to get out of that because of my work. But then being a physical, I think it's great for architecture schools to have people from all backgrounds. And Parsons was more so than I think most programs, but we had 50% people with undergraduate backgrounds in architecture and with any experience at all. And then 50% of us was like a history, someone had a master's degree in history, someone was a rhetoric major, there was like some art. So like, yeah, do it. It's good to have like a lot of backgrounds. And I think you need to have that other half that has the knowledge from undergrad. And it's definitely harder if you've never done it, like just getting used to the studio process. But yeah, it's great. Don't worry about it. Just try it.
Right, cool, thanks. Yeah, I've been worried, like if I would even have a shot at getting accepted, but you seem to definitely advocate for it.
Yeah, I mean, it is hard. Like you definitely, like I would recommend one of those programs and you can do it separate from school. Like it's a summer intensive. I don't know. Parsons had one. Columbia had one. I just know the ones on East Coast, but look and see if there's one in Denver, because they give you something to put in your portfolio too that you could use to show architecture schools that you deserve to get in, because that's the hardest thing for someone that, you're coming from out. If you have like an art background, you can show that stuff. If you've done construction or if you work for an architect, whatever it is, like you could show something, but coming from engineering, it might be hard to like show a portfolio of what you've done. That's the biggest hurdle. And you'll get in. So, yeah.
Okay, cool. Well, I'm gonna hop off, so thank you.
All right. See ya.
One last quick question. If I wanted to kind of reference more of the specifics of the guidelines of Passive House, where would I be able to find those? More like either reference
that's
kind
a
of
good question.
That, or is there like a website or a report that lists all these guidelines?
Well, yeah. So I didn't talk about this, but there's two governing bodies, and one is the Passive House Institute of the U.S. They're unrelated now. There's sort of like a schism. The Passive House Institute is based in Germany, and you can go to their website. I think if you just type in Passive Institute, you'll get their website, and it's like, I don't know, Germans, man. I shouldn't stereotype. The communication isn't that clear or that punchy or exciting, but it does, like, it has a lot of menus and you can kind of read more about it. But then the FIAS, so I'm trained by the Passive House Institute, so that's like what I know about more. And then FIAS actually has a lot more like built work in the US. And there was like a little, FIAS wanted to refine the like standard for different climate zones, which makes a lot of sense. And there was like a little like tension with the governing body over how that was going to be done. And so they just kind of split. But their website is like a little better designed, a little more compelling. And so I would recommend checking that out. And really the principles are all exactly the same. Those like criteria are all the same. You have to have all the same things, but the like 4.75 actually changes in Denver it's just a little bit with the FIAS metric, and the international standard, it's always that. So there's like but they both have the comfort criteria and they both have the same sort of like approximately the same level. So yeah, type in PHIUS. Sorry, I don't have.
No, that's all I needed. Yeah, thank you, appreciate it, and it was a really cool talk, and the graphics were really neat. So thank you.
Right. Good.
Thank you, Steve. Appreciate your time.
You bet. See ya.